All right, so I'm about to tell you the definition of measure, but first a couple more comments about this proposition. I want you to see that it points out kind of why being countably additive is awesome. It's awesome because it's the condition under which it makes sense to try to approximate sets by using countable unions of other sets. So remember when we were working with the Jorden measure? We had not defined measure, and we still haven't. We're about to, but we had this function that we refer to as the Jorden measure of a set, and it was specifically focusing on sort of x equals the unit interval, and we had our collection of elementary sets, which was an algebra of sets, and we had our Jorden measure defined on this collection. We wanted to extend the Jorden measure from this to a larger collection of sets. So not just elementary sets, but sets that can be approximated by elementary sets. The way to approximate is in this sense of sets going down onto other sets or building up to other sets like this, right? So countable additivity is going to be the condition under which so countable additivity of our Jorden measure on this, that's the condition under which when you try to extend to a larger collection of sets, everything remains consistent. So having our Jorden measure be when it was defined on this only, be countably additive was the crucial feature that made it possible to extend it to this larger collection of sets, which sadly was still not a sigma algebra, but it was better, right? The collection of Jorden measurable sets is much larger than just elementary sets. The countable additivity on here made the extension to here be consistent with these limiting properties that I'm referring to vaguely as continuous from below or continuous from above. So this is why we want countable additivity. And with that being said, here's finally the definition of measure, and this is actually the rest of definition 131, the one that defines additivity, countable additivity, those things. Or, sorry, actually it's the rest of definition 132. So if you have an algebra of sets on X and a countably additive function on it, then that's what we call a measure on this pair, which you might call a measurable space if this were a sigma algebra. So you can have, so this is set up so that you can still call something a measure when it's defined on something that's not a sigma algebra. So for example, the Jorden measure example from earlier can be called a measure even though it's not, what it's defined on is not a sigma algebra. But definition 135, a measure space is going to be a triple. So a set with 2 bits of structure. A set X, a sigma algebra, and a measure. So a measure space is a triple where you've got a set, you've got this is a sigma algebra on that set, and mu is a measure on that measurable space. But for a measure space, in our definition, we're going to require that mu always be non-negative. So instead of taking arbitrary just any real values, it has to take non-negative real values. So then we call it a non-negative measure. So a measure space is a measurable space, a set with a sigma algebra, along with a countably additive non-negative function on the collection of measurable sets. Or in short, a measure space is a measurable space equipped with a non-negative measure. Okay, so we finally defined the main object of study in this portion of the course in measure theory. So next time I'll start with the definition here, and we'll look at some trivial or silly examples, and we'll probably struggle to actually build up some seriously useful examples. And once we realize that, then we'll start developing some more theoretical tools.